Hello and welcome again to my physics online video lecture series. Today's lecture is going to be about the laws of reflection and refraction. This is, of course, for our algebra-based physics course. This is kind of the introduction to these topics lecture. So maybe a little bit of background before we get into the meat and potatoes of it, as it were. You've obviously all experienced at one point or another walking around outside, and there's a puddle on the ground, and you have sunlight streaming in. I guess I'm going to draw blue sunlight streaming in. And depending upon where you're standing, you certainly, no matter where you're standing, can see the sunlight kind of hitting this puddle and kind of bouncing off. So there's like reflections off in all random directions like this, so that no matter where you're standing, you can see the puddle and you can see little ripples and that kind of thing of it. But you've probably also experienced, and I'll switch over to yellow for this, you've probably also experienced that if you stand at a certain location relative to the puddle, that you can see kind of a bright reflection off of it from that particular location. And those of you who have had watches before, I don't have a watch, but if you have a watch, you may have done the thing where you're bored in class one day, you're sitting in the sunlight, and so you like twist the watch around and try to shine the little bright spot off of it onto a friend's face or something like that. So what's going on there? How is it that we have one area that's kind of very bright, and then yet at the same time from the rest of the room we can still see that there is a watch, we can still see that you're sitting in the sun and so on, that the sun is bouncing off of it, and for that matter with this pool of water? Well, we're looking at basically two types of reflection. Okay, so two types of reflection at play here. And both types actually exist in general. So any reflections that you see, there typically is a mix of the two. The first type is called specular reflection, and that's what's being represented here by our yellow lines. This is where you are using the watch to shine the bright light in your friend's face, or where you're seeing the bright glare off the puddle from the sun. This is, you could think of it as reflection from a smooth surface, and this is the kind of reflection that we're by and large going to be focusing on. But there's that second type, which is called diffuse reflection. And that diffuse reflection is reflection off of a microscopically rough surface. Okay, so even glass from your watch or even the puddle, they may even be macroscopically, in the puddle's case, rough, but microscopically they're both certainly rough. And essentially what's happening is you have light that's hitting the surface and just bouncing in all directions, because even though I've drawn this surface to be nice and smooth, and macroscopically it may well be, if you were to blow up this view many times over, the surface is not so smooth. And so you have, on the one hand, light maybe is incident like this here, and so it's bouncing off like this here. And then over here we have light, incident basically parallel to the first bit of light, but it's hitting a point where the curve is different. And so this light maybe bounces off more like this. And so you can see that even though we had parallel incident rays, we're not getting parallel reflected rays. So here's another parallel ray hitting here, and maybe this one happens to reflect off this way. But if we were to zoom way out, the surface is more or less flat, and so all the parallel lines come in and all the parallel lines reflect out more or less parallel to each other. Okay? So this brings us to what is the law of reflection say. So the law of reflection, and this is true for any individual ray, so whether we're looking at a diffuse reflection, whether we're looking at specular reflections, and the law of reflection basically says that if I have an incident angle, we'll call that theta I for incident, and I have a reflected angle, we'll call that theta R for reflected, the two should be equal to each other. There's actually a second part to the law that basically says incident, reflected, and normal are coplanar. This is the part that we typically focus on, though. So what does this thing mean? Again, let's draw our nice smooth surface, and this time we're going to draw only one ray incident on that surface. So here's my one ray. It's incident on this surface, and it reflects off of the surface. Okay, so this is incident. This is reflected. And then we need to define for ourselves these angles. And the way that we do that is we draw a line that is perpendicular to the surface. This is called the normal line. So this is normal line. It's perpendicular in all ways to surface. All right, so now we can define for ourselves those angles that we talked about. So this angle right here, from the incident ray to the normal line, this is our theta I for incident. This right here is theta R for reflected. Okay? And the second part of this law where it says that incident, reflected, and normal are coplanar, basically that's referring to this ray right here, this line right here, and this ray right here. All three are coplanar. So we're actually looking at a good representation of the three. They're all in the same plane. So if we call the plane the screen, then all three actually exist in the screen. They're not like pointing partially in or partially out. Okay. Now the second part of what we want to do today is what's called law of refraction. And so what that is all about is, let's say that I have two media. For example, maybe I have air here and I have water here. Now I send a ray of light from the air towards the water, like so. Instead of passing straight through like this right here would represent the ray going straight through the surface and not deflecting at all. The ray actually bends at this interface, like this. This second black dashed line is again normal to the surface, which means normal on both sides to the surface, incidentally. Then we can define for ourselves two angles once again. Let's maybe put them in green. So we have angle 1, we'll call that theta 1. We have angle 2, we'll call that theta 2. And the law of refraction, this is also called Snell's law. Snell's law of refraction governs how these two angles are related to each other. And the equation that governs them basically says that a quantity N1 times sine of theta 1 is equal to N2 times sine of theta 2. So now you may be wondering, what are N1 and N2? Well, we'll define N1 and N2 to be what are called refractive indices. So N1 and N2 are refractive indices, or index of refraction. Indices, plural for index. And these are the indices of refraction for the two media. So we'll say medium 1, for example, air, and medium 2, for example, water. So what is the refractive index then? That's a little bit more complicated. It basically pertains to what's called the polarizability of the medium. And specifically, its polarizability is a complex number, the imaginary part of which gives you your refractive index. For our purposes, though, there's a simpler definition. Basically, N, we'll say N sub j, so N for medium j, is equal to the speed of light in vacuum divided by the speed of light in that medium. So again, this refractive index, for simple purposes, is essentially telling us how slowly or quickly light will travel through the medium. So you take the speed of light in vacuum, which is always given by the same number. If you want the full number, 2.9979245 times 10 to the 8 meters per second. And then you divide it by the speed at which light actually propagates through the medium in question. And that gives you, for most media, that gives you what the refractive index will be. Now, I have that caveat for most media because there are some media, such as plasmas, where this law doesn't quite hold. But for most of the media that you'd encounter in a Physics 2 course, introductory physics course in general, you're looking at like water or air or glass, or basically a liquid, a solid, or a gas. This generally holds true. Okay, so very simple example for water. So example, water has refractive index about 1.3, sometimes about 1.33. So the speed of light for water, C for water, must be, rearrange this equation, you have C0 divided by in water. And so this number right here, for approximation purposes, is about 3 times 10 to the 8 meters per second. So we have 3 times 10 to the 8 meters per second divided by 1.33. And that gives us approximately 2.2556. So let's call that 2.26 times 10 to the 8 meters per second. It's the speed of light in water. Now, to get these refractive indices, you usually end up looking them up from a table, which is often included in your textbook. Some common ones: vacuum is exactly 1, air and most gases a little bit more than 1, like 1.00, etc.